Hello friends, I welcome you all to this session on power plant engineering. So in the last lecture, you have learned that how energy from the coal converts into electrical energy. What are the different components? So today what we'll do is we will learn about the cycle which runs at the heart of any steam turbine power plant. So that cycle is what we call as Rankine cycle. Now, for each and every process whatsoever we have seen in the previous lecture, which is acting between, let's say, boiler and turbine, turbine and condenser and pump and boiler, we can assume a ideal process, a hypothetical process, which represents the basic operation and does not produce any extraneous effect. So we can assume a hypothetical process with no friction, no dissipating effect and at all. So for that matter, let us consider the same diagram but with a different philosophy. Now, if you look, there is a turbine. So that is how we represent a turbine. So this is a turbine, that is a work producing component. So let's say steam at a high pressure and temperature enters here at state 1. Then from here it will move to condenser where the heat loss will takes place. And what is happening here? So this is basically a cooling tower. So energy is being lost here. Now this is now liquid. So this moves to pump which supplies this to the boiler. Now boiler is not a simple drum. There are so many components. So what we can do is we can draw these components. So here it will enter. So there are several components, but majorly we can draw them. Now, so this, let's say, is state 2. Then after condenser, let's say this is state number 3. Then after pump, this is 4. And now the water into a portion where it is first preheated, and that is called as economizer. That is the one which adds into the economy of a power plant, because what we do is we don't allow these gases, flue gases which are going out, to directly move out. So first we transfer them to economizer so that their energy is still remaining with them, that can be used to heat up the water. Okay. Then comes the evaporator. That is that portion where the real conversion of water to steam takes place, and then that steam is further heated in superheaters so that their energy can be increased and the temperature can be increased at the same pressure. So let's say this is state number 5, this is state number 6, and that is 1. So here inside, from the furnace, the flue gases are entering. This is flue gas, and here they will exit and move to the chimney stack. High temperature flue gases enter, assume 1250 degrees Celsius, and leaves at around 120 130 degrees Celsius. So this is not important. This part, this cycle is important. So one by one we'll understand. Okay, now what is happening here? Inside turbine, the steam at low pressure is being converted into high pressure is being converted into low pressure. That means the energy of the steam drops. So now if I write inside turbine, what happens? The process turbine, the process can be thought of as reversible plus adiabatic. That is isentropic. Process happens. Now inside the condenser, the condensation process ideally can be reversible plus isobaric. That means constant pressure. Okay, then inside pump, we can also assume frictionless adiabatic process, that is again isentropic process. Isentropic. So then inside this is pump, then comes boiler. So the heating process can be thought of as reversible plus isobaric. So every process whatsoever is happening inside, we are thinking that it is happening ideally. So that all will constitute your Rankine cycle. Now, if you draw that in TS diagram, temperature entropy diagram, then this is your vapor dome. Okay. Now let me draw it with red color. So this is a constant pressure process, higher side, and this is a constant pressure process, lower side. That means this is a high pressure, can be thought of as a boiler pressure. Okay, let's say P1, and this is a or boiler pressure, and this is P2, can be thought of as condenser pressure. So now initially the state of the steam is here 1. Then from here the expansion happens reversible adiabatically in the turbine. Let's say this is the 1. So in this process the shaft work is generated, and the steam from high pressure steam to a low pressure steam conversion happens. Then comes the condenser. So this is 3. So here the steam at which is in very close to saturated vapor or slightly inside the dome gets converted into saturated liquid, and this happens via release of latent heat of condensation. So let us say this is Q2. So here inside this there is a heat loss, Q2 happens. Okay, then comes pump, where we will be supplying pump work. Let's say W dot P. Okay, so this is dot. Then comes pump. So reversible adiabatic compression here happens. So this is state number 4. So this is basically W dot P. Then the state from now it is 4. Then from 4 it moves to economizer, where the constant pressure heating takes place up to saturated liquid state. So this is the 1. This is 5. Then from 5 to 6 there is phase change from liquid to vapor. So this is 6. And then from 6 to 1 there is superheating from saturated vapor to the superheated vapor, and that happens here in superheater. So that is what your Rankine cycle is in case of in TS diagram. Similarly, you can also draw the same cycle in PV diagram or in HS diagram. So let us do that also. So let us draw this in PV diagram. So this is the vapor dome in case of PV diagram. So this is your boiler pressure, this is your condenser pressure. Now this is state number 1. Let me take red pen. So here the reversible adiabatic expansion takes place. This is 2. Then this is basically shaft work production. Then the heat loss in the condenser. This is Q2 dot. Then this is pump work, and then finally the heat transfer in the boiler. So this is Q1 dot. So in totality from 4 to 1, the amount of heat transfer is Q1 dot. The same thing you can also do here in HS diagram as well, enthalpy entropy diagram, which is also called as Mollier diagram. The Mollier diagram is like this. The critical point is here the critical point is at the top, and in TS diagram also it is at the top. So now two constant pressure lines. So this is the one high pressure and this is low pressure, and this is state number 1. So reversible adiabatic. So this is the one turbine process where we will be getting the shaft work. Then this is point number 3. This is heat loss Q2 dot. Then this is the pump work, and this is basically the heat input in the turbine. So in this way, friends, you can represent your steam processes in a steam power plant via the temperature entropy, pressure volume, or enthalpy entropy diagrams. Now, normally I prefer temperature entropy diagram. So, what I'll do now, or in the next lecture, what we'll do, in the next lecture, we'll try to find out the energy interactions in different processes occurring in the Rankine cycle. So, in this lecture, till this point only, thank you very much for watching it.